Introduction. Students, do you know what integers are? A whole number that can be positive, negative or zero. Correct. And what are whole numbers? The set of numbers that include 0 plus the set of natural numbers. Good. Today we will learn about real numbers. Real numbers consist of rational and irrational numbers. Real number system has many subsets: integers, natural numbers and whole numbers. Come, let's study real numbers in detail. Objectives. At the end of this lesson, you'll be able to explain Euclid's division lemma, explain the fundamental theorem of arithmetic, solve questions by using prime factorization method. Euclid's division lemma. Euclid's division lemma states that for any two positive integers a and b, there exists unique integers q and r such that a is equal to bq plus r. 0 is smaller than or equal to r, which is smaller than b. For example, a is equal to 15, b is equal to 3. It is observed that 15 is equal to 3 into 5 plus 0, where q is equal to 5 and r is equal to 0. Lemma. A lemma is a proven statement used for proving another statement. An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Euclid division algorithm can be used to find the SCF of two numbers. It can also be used to find some common properties of numbers. How to obtain HCF? To obtain the HCF of two positive integers, say c and d, with c is greater than d, we have to follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So, we find whole numbers q and r such that c is equal to dq plus r. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Example of HCF calculation. Let us find the HCF of 455 and 42 using Euclid's algorithm. Solution. Since 455 is greater than 42, we apply division lemma to 455 and 42 to get 455 is equal to 42 into 10 plus 35. Remainder is not 0, therefore we apply lemma to 42 and 35. 42 is equal to 35 into 1 plus 7. Again, the remainder is not 0, therefore we apply lemma to 35 and 7. 35 is equal to 7 into 5 plus 0. We can see that the remainder has become 0 and we cannot proceed any further. Therefore, the SCF of 455 and 42 is the divisor at this stage. Example of Euclid theorem. Let us now prove that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Solution. Let a be any positive integer and b is equal to 2. Then by Euclid's division lemma, there exist integers q and r such that a is equal to 2q plus r, where 0 is smaller than or equal to r is smaller than 2. Now, 0 is smaller than or equal to r is smaller than 2, which implies 0 is smaller than or equal to r is smaller than or equal to 1, which implies r is equal to 0 or r is equal to 1 because r is an integer. Therefore, a is equal to 2q or a is equal to 2q plus 1. If A is equal to 2q, then A is an even integer. We know that a positive integer can be either even or odd. Therefore, any positive odd integer is of the form 2q plus 1. The fundamental theorem of arithmetic. The basic idea is that any integer above 1 is either a prime number or can be made by multiplying prime numbers together like this. Let us start with the definition. Any integer greater than 1 is either a prime number or can be written as a unique product of prime numbers, ignoring the order. Look at these numbers. Relationship between LCM and HCF. For any two positive integers a and b, HCF AB into LCM AB is equal to a into b. Example: if a is equal to 3 and b is equal to 6, HCF 36 into LCM 36 is equal to 3 into 6 equals 18. This result can be used to find the LCM of two positive integers if we have already found the HCF of the two positive integers. We can find that HCF and LCM of the two numbers with the help of the prime factor. Let us see how. Find the LCM and HCF of 510 and 276. 510 is equal to 2 into 3 into 5 into 17. 276 is equal to 2 into 2 into 3 into 23. The common factors of 510 and 276 are 2 and 3. Thus, the HCF is equal to 2 into 3. For finding LCM, write common factors once and then write remaining prime factors of each number. Then multiply all these and you will get LCM of the given number. 510 is equal to 2 into 3 into 5 into 17. 276 is equal to 2 into 2 into 3 into 23. The common factors are 2 and 3 and the remaining prime factors of 510 are 5 into 17 and remaining prime factors of 276 are 2 into 23. Thus, LCM of 510 and 276 is equal to 2 into 3 into 5 into 17 into 2 into 23 equals 23,460. Let us see what is the relation between the product of LCM and HCF of the two numbers and the product of two numbers themselves. From the above discussed example, product number is equal to 510 into 276, which equals 1,40,760. Product of HCF and LCM is equal to 23,460 into 6, which is 1,40,760. Thus, product of HCF and LCM is equal to product of numbers. More accurately, for two given numbers a and b, HCF AB into LCM AB is equal to a into b. Example: the LCM of two numbers is 126. If one number is 18 and HCF of the numbers is 2, find the other number. We know that product of two numbers is equal to product of their LCM and HCF. That is, 18 into x is equal to 126 into 2. Here, x is the other number. That is, x is equal to 126 into 2 upon 18. That is, x is equal to 14. Examples of fundamental theorem of arithmetic. Given that HCF 306, 657 is equal to 9, find LCM 306, 657. Solution. We know that the product of HCF and LCM of two numbers is equal to the product of the given numbers. Therefore, HCF 306, 657 into LCM 306, 657 is equal to 306, 657 is equal to 9 into LCM 306, 657 equals 306, 657, which is equal to LCM 306, 657 equals 306 657 upon 9. LCM is equal to 22,338. Did you know? In the 17th century, Descartes introduced the term real to describe roots of polynomial, distinguishing them from imaginary ones. Carl Friedrich Gauss is often referred to as the Prince of Mathematicians and is considered one of the three greatest mathematicians of all time, along with Archimedes and Newton. He has made fundamental contributions to both mathematics and science. Summary. Let us summarize what we have learned. Euclid's division lemma. Given positive integers a and b, there exist whole numbers q and r, satisfying a as bq plus r, 0 is smaller than or equal to r is smaller than b. Euclid's division algorithm. This is based on Euclid's division lemma. According to this, the SCF of any two positive integers a and b, with a is greater than b, is obtained as follows. 1. Apply the division lemma to find q and r, where a is equal to bq plus r, 0 is smaller than or equal to r, which is smaller than b. 2. If r is equal to 0, the SCF is b. If r is not equal to 0, apply Euclid's lemma to b and r. 3. Continue the process till the remainder is 0. The divisor at this stage will be SCF AB. Also, HCF AB is equal to HCF BR. The fundamental theorem of arithmetic. Every composite number can be expressed factorized as a product of primes, and this factorization is unique apart from the other in which the prime factors occur. Look at these numbers. Do you know what do we call these numbers? These are the real numbers. Teacher, is an irrational number is also a real number? Yes, an irrational number is also a real number. A rational number or an irrational number is called a real number. Today we will learn more about rational as well as irrational numbers. Objectives. At the end of this lesson, you will be able to define irrational numbers, show whether the number is irrational or not, explain rational numbers and their decimal expansions, convert the rational numbers into decimal expansion. Revisiting irrational numbers. We know that rationals and irrationals together made up the real numbers. A number S is called irrational if it cannot be written in the form P upon Q, where P and Q are integers and Q is not equal to 0. Irrational means not rational. The most famous irrational number is square root 2. Other examples are pi, which is equal to 3.141592 and 0.1011011110 1110 and so on, etc. Theorem related to irrational numbers. Theorem. Let P be a prime number. If P divides a square, then P divides a, where a is positive integer. Let us prove this theorem. Proof. Here we will firstly find the prime factorization of a. That is, a is equal to P1, P2, so on till Pn, where P1, P2, and so on till Pn are primes, not necessarily distinct. Therefore, a square is equal to P1, P2, and so on till Pn. P1, P2, and so on till Pn is equal to P1 square, P2 square, and so on till Pn square. Now, as it is given that P divides a square, therefore, from the fundamental theorem of arithmetic, we can say that P is one of the prime factors of a square. Also, we realize that the only prime factors of a square are P1, P2, and so on, Pn. So P is one of the P1, P2, so on till Pn. Now, since A is equal to P1, P2, so on till Pn, we can say that P divides A. Theorem. Let us now prove that square root 2 is irrational. Suppose square root 2 is rational. That means it can be written as the ratio of two integers P and Q. Square root 2 is equal to P upon Q, which is equation 1, where we may assume that P and Q have no common factors. If there are any common factors, we cancel them in the numerator and denominator. Squaring in 1 on both sides gives 2 is equal to P square upon Q square, equation 2, which implies P square is equal to 2Q square, equation 3. Thus, P square is even. The only way this can be true is that P itself is even. But then P square is actually divisible by 4, hence Q is square, and therefore Q must be even. So P and Q are both even, which is a contradiction to our assumption that they have no common factors. The square root of 2 cannot be rational. Example. Let us solve an example now. Prove that 1 upon square root 2 is irrational. Prove. Let us assume to the contrary that 1 upon square root 2 is rational. That is, we can find coprime A and B where B is not equal to 0 such that 1 upon square root 2 is equal to A upon B. Therefore, B upon A is equal to square root 2 or square root 2 is equal to B upon A. Since A, B are integers, we get B upon A is rational and so square root 2 is rational. But this contradicts the fact that square root 2 is irrational. This contradiction has arisen because our incorrect assumption that square root 2 is rational. Example. Prove that 7 square root 5 is irrational. Let us assume to the contrary that 7 square root 5 is rational. That is, we can find coprime A and B where B is not equal to 0 such that 7 square root 5 is equal to A upon B. Therefore, A upon B upon 7 is equal to square root 5 or square root 5 is equal to A upon B upon 7. Since A, B are integers, we get A upon B upon 7 is rational and so square root 5 is rational. But this contradicts the fact that square root 5 is irrational. This contradiction has arisen because of our incorrect assumption that 7 square root 5 is rational. Revisiting rational numbers and their decimal expansions. As you may remember from school, rational numbers have a terminating or eventually repeating periodic decimal expansion, whereas irrational numbers don't. So, for example, 0.123, 123, 123, 123, and so on, with 123 repeating forever is rational. In fact, it is equal to 41 upon 333. Whereas something like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on, which will never repeat, is irrational. Terminating decimal. If the number of digits after decimal is finite, is a terminating decimal. Example, 2.57, 3.1925, 0.333. Non-terminating decimal. If the numbers of digits after decimal are infinite, then it is a non-terminating decimal. Theorem related to rational numbers and their decimal expansions. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p upon q, where p and q are coprime and the prime factorization of q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. For example, 0.1837 can also be written as, we know that the rational number P upon Q can be converted into decimal representation by using long division method by dividing P by Q. Look at this example now. Here we can see that a rational number of the form P upon Q, where Q is of the form 2 raised to the power n, 5 raised to the power m, is converted to an equivalent rational number of the form A upon B, where B is a power of 10. The decimal expansion of such a rational number terminates. One more thing to note is that a terminating decimal can also be thought of as being followed by an infinite sequence of zeros. So in this sense, even terminating decimals are actually periodic. Theorem. Let x is equal to P upon Q be a rational number such that the prime factorization of Q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let us solve an example. Without actually performing the long division, state whether the following rational number will have a terminating decimal expansion or a non-terminating repeating decimal expansion. 13 upon 3125. We can write it as 13 upon 3125 is equal to 13 upon 5 raised to the power 5. Here Q is 5 raised to the power 5, which is of the form 2 raised to the power n, 5 raised to the power m, n is equal to 0, m is equal to 5. So the rational number 13 upon 3125 has a terminating decimal expansion. Let x equals P upon Q be a rational number such that the prime factorization of Q is not of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, recurring. Let us now write the decimal expansion of 17 upon 8. Similarly, decimal expansion of 15 upon 1600 is 0.009375. Did you know? The word algorithm comes from the name of the 9th century Persian mathematician Al-Khwarizmi. Even the word algebra is derived from a book he wrote called Hisab al-Jabr wa al-Muqabala. Summary. Let us summarize what we have learned. Let x be a rational number whose decimal expansion terminates. Then we can express x in the form P upon Q, where P and Q are co-prime, and the prime factorization of Q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Let x is equal to P upon Q be a rational number such that the prime factorization of Q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let x equals P upon Q be a rational number such that the prime factorization of Q is not of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating.